how simple these proofs are, and I'm usually right. All right, so just like I did yesterday when we were talking about what it means for figures to be congruent and comparing that to what we were talking about yesterday and what it means for figures to be similar, I am also flashing back in today's lesson to chapter 4 again. And remember that in chapter 4, that's when we had the big proofs push. And we were proving that triangles were congruent. And remember that I gave you a lesson about the shortcuts. And there were a lot of S's and A's on that screen. You may recall side, 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 angle, angle, and angle, angle, side. And I brought your attention to what combination of S's and A's did we not see on the screen? And some of you had the little giggle. Yes, it was the naughty word. There was that. But there was also angle, angle, angle. And you may recall, hopefully, that I told you angle, angle, angle doesn't work because while it guarantees that the triangles will be the same shape, it doesn't guarantee that they'll be the same size. And now in chapter 7, it's convenient to recall that because, as I mentioned yesterday, figures that are similar are basically the same shape, but not necessarily the same size. You may be noticing in our first bullet that angle-angle similarity is the first means by which I can prove that two triangles are similar. Okay, so if I know that two pairs of their angles are congruent, that's enough. I can say that those two triangles are similar. I'm going to kind of jump around. Side-side similarity is probably the next easiest to make sense of. Side-side similarity means I don't necessarily know anything about the angles, but I could show that all three pairs of sides are proportional. The last one is side-angle side. And hopefully what you remember from chapter 4 about side-angle side kind of carries us over into this chapter where I'm dealing with two pairs of sides, and the angle that's important to me is the angle formed by those sides. Now the angles are still going to be congruent just like they were in chapter 4, but here since these figures aren't necessarily congruent, they are similar, those two pairs of sides are going to be proportional. Okay, so we're starting off. Okay, let's take a look at problem 2 before we bounce back to the your turn for problem 1. In problem 2, kind of along the same lines, except now if the triangles are similar, I want a similarity statement. So in part A, are the triangles similar? What math might I have to do here in order to determine that? Oh, math. Yeah, I got to set up my ratios and see if they're equivalent. So 24 over 12 would need to be equivalent to 10 over 5 and 26 over 13. And they are equivalent. So yes, the triangles are similar. And it's not asked of us up in here, but in the interest of making our notes as thorough as possible, I would encourage you to write down why these triangles are similar. Why are they similar? Side, side, side similarity. And then we were asked for a similarity statement. That's triangle what is similar to triangle what? How would I name these triangles? Yep. How about the triangles in part B? What math might I have to do here in order to determine whether these triangles are similar? You do see the two triangles, yes?
Well, let's do your trapezoid. Your trapezoid with a hat.
Always 10.
Look, it's as I had it.
You see the two triangles now?
Yes.
Oh, yeah. me just put him aside for a moment. So what math, coming back to that question, what math would I have to do in order to determine if these two triangles are similar? Good. Okay. When we set up our ratios, you cannot just do 12 over 4.8. Because as Taylor so wonderfully pointed out, that 4.8 isn't a side of the triangle, that's a side of the trapezoid. Okay? So we would have to check if 12 over 16.8 is equivalent to 10 over 14. And oh darn, that's only two pairs of...
What's the angle, Miss Clouse?
Yes, angle T, notice, is the angle between those sides. And angle T is congruent to itself, and it's an angle in both triangles. So, are the sides proportional? Do they work out?
I don't know.
They are. So, yes, the triangles are similar, and by side angle side similarity, yes. And once again, we're asked for a similarity statement. So triangle what is similar to triangle what? Triangle RTV is similar to triangle STU. And if there's anything on the screen that you have a question or confusion about, you know I want to go over it before proof. All right. So, everybody's favorite thing in the whole wide world. Oh my goodness. All right, hurry up. Oh, you just want to tell me? Tell me. No, just tell me. No, you know what? In the interest of time, I'm taking all the fun out of it.
Only 20 minutes left.
Agony. Yeah, but problem 4 is pretty beefy. All right, so, of course, I know where I start my proof. I start it with my given. Next, I look at what I'm trying to prove. I'm trying to prove that these two triangles are similar. And then I remember I have 3 ways of showing that triangles are similar. Either angle-angle, side-side-side, or side-angle-side. What you need to realize is that side-side-side and side-angle-side both require that I know side lengths or some relationship between those sides. Do I have that in my given? No. All I have is parallel lines. And what I hope your brain, the trigger that I hope your brain catches is that parallel lines was chapter 3. Remember the parallel lines and the alternate interior, alternate exterior, all of that stuff. So, in the context of that, am I refreshing your memory, Benjamin? Angle C and M are not vertical angles, nor are P and A. Taylor? Well, they are congruent, but I'm not using the definition of congruent angles. Yes. Oh, Aria heard me say that. They're alternate interior angles. And now that I have 2 pairs of congruent angles in these triangles, why are these triangles similar? Angle-angle, yes. But problem 3 is asking us something further in part B. Then it's asking us, suppose you were only given those 2 pairs of proportional sides. Let's visualize them. That would be CA is to PM as CB is to MB. If that was all I had, would I be able to say that these triangles were similar? Yes or no? But I only have two pairs of proportional sides. I either need three pairs of proportional sides, or I need the angles between those sides to be congruent. I wasn't given that in this supposition in part B. However, okay, so my bottom line answer to part B is no, you wouldn't have enough information. You would need to also have been given that angle C is congruent to angle N. However, here's a point that I want to bring up. Suppose that I still had that MB is to CB as, this time, these sides were proportional. Suppose I had those two pairs of proportional sides in the triangles. Would I be able to say that those triangles are similar? Yes. Why? No, I'd have two pairs of sides still, but yes, the angles between those sides would be congruent because of the vertical angle theorem. Okay, so be able to make those connections, ladies and gentlemen. All right? Last problem. There's Benjamin. Okay, and you're looking at this, and some of you, oh, words. I like words elsewhere, but words and numbers, I just don't like them together in this house.
It's only there.
Well, there's that too. Okay, but, you know, I'm trying to push that love of numbers into you, you know, a la fuerza, as we say. All right. So, all right, so Benjamin places a mirror 40 feet from the base of an oak tree. So let's visualize. I've got this oak tree, and Benjamin places a mirror 40 feet from the base of it. So there's my 40 feet. And then, when he stands 5 feet from the mirror, ooh, he sees it. Lovely. Here's Benjamin.
Every math problem with a tree equals a triangle.
There's Benjamin. Standing 5 foot 8 inches.
That's actually really accurate.
And what we're trying to do is find the height of the tree. And Taylor already noticed that, yes, we have triangles here. And what we need to realize, we have enough of you engineering people in here that you probably already know this, the property that they're using here is the fact that, guys, when you're looking into a mirror, the angle, basically, angle in is congruent to angle out. And since Benjamin is standing on the ground and he is therefore perpendicular to the ground, similarly, the triangle is perpendicular to the ground. We see that Benjamin's triangle is similar to the tree's triangle. Yes, sir?
So because it's a mirror, the angle is congruent.
Yes.
It's not math.
Math.
It's
application.
How are you like knowing that a mirror gives off two congruent?
Because I'm telling you.
But you didn't tell us.
Why wouldn't I? Because I'm the Clouse.
No, like it was on
and
the
I'm thorough.
test. I'm not like on your test, like the end of course exam. Was you stupid?
It's expected that your teacher is covering it. Am I covering it?
Yeah.
Yes, so we're good. Okay. So, in order to figure out the height of this triangle, or the height of this tree, I need to set up and solve a proportion. And now, looking at the measurements, do you see a problem with the problem?
No.
What's the problem with the problem, Benjamin? What's the problem with Benjamin?
Yeah.
Right, the feet and inches is kind of yucky. So let's convert Benjamin's triangle into inches. Okay, so this is 68, and this is 60. Now, some of you might be thinking, why don't I convert everything into inches? And the reason is, if I leave the tree triangle in feet, and I have Benjamin's triangle in inches, because the triangles are similar, the ratios will still be the same. It'll still work out, and when we solve our proportion, everything will come out in feet, and it'll be nice and pretty. Okay? So, what will my proportion look like? What over what equals what over what? 60 over? Yes. Equals? That's it. Cross multiply and solve. And very possible, yeah.
It was like, here's the flagpole, and then it gives off the shadow.
Right, and that's another kind of problem that you might encounter in your homework is shadow problems. Right, so 60x equals 2720. Okay, so 2720 divided by 60, and I have 45.3 repeating. Okay, but looking at this 45.3 repeating feet, I don't know about you, but I don't like that 0.3 repeating when we're talking about feet. So what is 0.3 repeating? No. 0.3 repeating. No. A third, right, a third. 0.3 repeating is equivalent to 1/3. And what I'm looking for here in this problem is what is 1/3 of a foot? So it is 1/3 of a foot. Michael? It's 4 inches. So the prettier answer that you might want to give here would be 45 feet and 4 inches. And that is the height of the oak tree.